So, transition metals. Hopefully we all know that the periodic table is split up into different blocks: S block, P block, D block, and then there is the F block, which we've not shown on here. S block is group 1 and group 2, P block is 3, 4, 5, 6, 7, and 0, and D block is that middle block. We also can refer to the majority of those middle block, D block elements, as transition metals, but not all of them. We're about to go through it, but just have a quick think. Why can we not define scandium or zinc? Why can we not call them transition metals? They're still D block elements, but they're not transition metals, unlike the majority of the metals in the D block. Why not? Well, first thing we need to think about is the definition of a transition metal. A transition metal is a D block element that forms at least one stable ion with a partially filled d orbital. You can replace d orbital with d subshell if you want there, but d orbital is also technically correct. So transition metals are D block elements that form at least one stable ion with a partially filled d orbital. They need, in order to be called a transition metal, they need to have this stable ion that is stable with a partially filled d orbital. D orbitals can hold up to 10 electrons. There are 5, so that's incorrect. Sorry, that should say the d subshell can hold up to 10 electrons. A d orbital is an orbital is the place where 2 electrons can exist. So the d subshell can hold up to 10 electrons because it has 5 orbitals. Each orbital can hold 2 electrons, so that's a total of 10. So sorry, just change that on your notes if you need. Scandium and zinc are not transition metals because the only ion that scandium can form is Sc3+. And the only ion that zinc can form is Zn2+. So they can form stable ions. Why are they still not transition metals? Because they don't have a partially filled d orbital or a partially filled d subshell. Let's prove it to ourselves. Scandium, as an atom, has got 21 electrons. When it forms an Sc3+ ion, how many electrons has it lost? Or what's happened to its electron configuration? It's only got 18. It's lost 3 electrons. If you were to fill in the electron configuration for, actually, let's change colour for that one. Let's do that in red. If you were to fill in the electron configuration for scandium, for a scandium atom, we would have, this is our 4s, this is 3d. We would have 4s2, 3d1 would be scandium, 4s2, 3d1. That's normal electron filling rule. So for the scandium atom, it's 4s2, 3d1. For the ion, 3d, Sc3+, we lose those upper 3 electrons, the highest in energy. And in this case, the highest in energy is 1, 2, 3. The 2 from 4s and 1 from 3d. So our scandium ion has got no electrons in the 4s or 3d orbital. That means that it has an empty d subshell or empty d orbital. It doesn't have a partially filled d orbital. It doesn't have a partially filled d subshell either. So it cannot be a transition metal. It does form a stable ion, but its stable ion, its only stable ion, does not have a partially filled d orbital or a partially filled d subshell. Zinc. What about zinc? Zinc has got, a zinc atom has got a total of 30 electrons. A zinc ion, Zn2+, has lost 2 electrons, so it will then have 28 electrons. Again, within zinc, the atom electron configuration should look something like this. That is what the zinc atom looks like. But when it loses 2 electrons to become a zinc ion, Zn2+, it loses its highest energy electrons, which once filled, the 4s orbital is higher in energy than 3d, so it loses the 4s orbital electrons, leaving it with a full d subshell. Again, not partially filled. Oops, I meant to write subshell there. Again, not partially filled. So it also cannot be a transition metal. Hopefully everyone is happy with that. Let's have a think about that 4s3d thing then, because that's a little bit confusing. We've got two elements which use this theory. You don't have to be able to explain the theory, but you have to know what their electron configuration is, and that is chromium and copper. The way I remember it is two outer C elements. So there's chromium, cobalt, and copper. The two outside ones are the ones that have the weird, or what we think of as weird in their electron filling. It's actually not weird. It's very makes sense theory-wise when we go through it, but it does feel weird. So why is that? Why are their electron configurations different? So when we're filling electron configurations, you always fill lowest energy first. So lowest energy subshells or orbitals fill first. I'm trying my best to use, by the way, the terms subshell and orbital only when they can be used interchangeably. They do mean different things. An orbital, I'm specifically talking about the space in which two electrons can exist. A subshell is the collection of all of the orbitals in that subshell. And then a shell is just all of the subshells together. So I'm trying to use those terms only when it's possible to use both. So I'm trying to use them interchangeably when it is correct to use them interchangeably. I do my best. What was I saying? Yes, so we fill orbitals and subshells from lowest to highest in energy. So we would always fill lowest first. And when the 4s subshell, what is also an orbital because it's only an s orbital on its own, when that is empty, it is actually lower in energy than the 3d subshell. You can see here, this 4s is lower than the 3d, which means we fill it first. Makes sense, because we fill lowest to highest. Actually, let's change the color of that one. Let's make that 3D so we can see the difference. So it makes sense. We fill lowest first. The trouble is, so 4s will fill up with electrons first before 3D. The trouble happens when it is full, it is higher in energy. It actually shifts to become higher in energy than 3D once it is full. And that's why we then continue to fill in 3D until that is full. And it is also why 4s loses electrons first. So once it's full, it is actually higher in energy. And therefore we lose electrons from 4s first before 3D. They actually switch in terms of, switch places in terms of their comparative energy. But chromium and copper, they don't technically, they behave differently in terms of what their electron configurations look like. They actually follow all the same rules. Because 4s loses electrons first before 3D, when you come to do, let's do chromium first. When you come to do chromium, a chromium atom, 1, 2, 3, 4, 5, technically should have 6 electrons in, no, it shouldn't. I've just done that wrong, sorry. Technically, we should fill, I've just done the other one first. Technically, we should fill the 4s first, 1, 2, and then we should fill chromium 3, 4, 5, 6. But what happens, because 4s is higher in energy, so these are our 4s electrons, this is 3D, because 4s is higher in energy than 3D, by allowing an electron to drop down into a 3D orbital, the substance, chromium, will, by allowing an electron to give off some energy and fall down into a lower energy orbital, the chromium atom has lost energy and therefore become more stable. So chromium atoms demote an electron down to a lower energy orbital in order to make themselves more stable. Hence, their electron configuration looks different to other ones because the theory is all the same between atoms. It's just these guys can take advantage of that theory and it can demote an electron. By doing that, it makes itself more stable. Copper is the same. It follows the same principle. Copper should have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 electrons in its 4s and 3d orbitals. But it can also demote an electron. it can allow an electron to release some energy and drop down to a lower orbital, and in doing so makes itself more stable and therefore has slightly what we would consider to be different or odd electron configuration. So the electron configuration of chromium can be written as 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, 4s1. So it's got 2 half-filled orbitals. And copper, 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d. That should be 3d10. There's an error there. That should be 3d10. So I don't know why it says, oh, sorry. No, sorry. I realized I've read that wrong. My fault. I read the box wrong. The electron configuration of chromium can either be written 3d5 4s1 or 4s1 3d5 is what they're saying. Sorry. Doesn't matter which order you write the end to shell / subshell denotions in. Technically, if it were me, I would be putting 4s first, then 3d5, because I like to write it in order of increasing energy. But if you want to write it in order of keeping shells together, then you might want to write 3d first and 4s. You will get a mark for either in an exam. They're both correct. Apologies, just to clarify, the electron configuration of copper would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10 for copper. Okay, I think that's all I wanted to say. So I'm also just going to put that's empty. The empty 4s subshell is lower in energy than the 3d subshell. The full 4s subshell is higher in energy. Hence, it makes sense. You don't have to be able to explain this. You just need to be able to write the electron configuration for chromium, and copper and their ions.